Hey everyone! Today we're going to tackle one of the most powerful, but yet often super misunderstood tools in concurrent programming, the semaphore.
All right, so you've probably heard this before, right? A mutex is like one key for one lock. Simple. So it kind of makes sense that a semaphore is just a whole bucket of keys, right? Well, stick around because the real answer is way cooler and a lot more useful.
So let's dive into that whole bucket of keys idea. Because honestly, the best way to really get what a semaphore does is to first see why that popular explanation, well, kind of falls flat on its face. Okay, so picture this, the classic coffee shop analogy. A mutex? That's the key to the single restroom. Only one person has the key, only one person can go in at a time. Makes sense. The analogy then says a semaphore is like having a whole bucket of keys for, say, 3 identical restrooms. Seems logical enough, doesn't it? Yeah, but hold on. While that sounds neat on a whiteboard, in the real world of code, that analogy has a huge critical flaw that pretty much makes it useless. Think about it. This is where it all falls apart. You walk up, you grab a key from the bucket, now what? How do you know which of the 3 restrooms is actually empty? You'd have to go and try your key on every single door until one opens? That's super inefficient. You'd basically need another system on top of the keys to tell you which room is free. So yeah, the whole bucket of keys thing, it just doesn't work. Okay, so let's just toss that whole bucket of keys idea out the window. Forget it. To really understand a semaphore, we need to see it for what it actually is. And at its heart, it's just a protected counter. So what does that mean? A semaphore is really just a special variable, a number. You can add to it and you can subtract from it. But here's the magic trick. These operations are atomic. That's a fancy way of saying they are uninterruptible. When a task goes to change that number, nothing else can interfere until it's done. That's what keeps everything from turning into chaos. All right, let's walk through a real example. Imagine we have some kind of resource, maybe a few network connections, and we can only have 3 tasks using them at the same time. So we'll set up our semaphore and initialize its count to 3. Okay, here comes task A. It needs access, so it does what's called a take or wait on the semaphore. The semaphore checks its count, it's 3, which is more than 0, so great. Task A gets access, and the count immediately drops down to 2. Right behind it is task B. It does the exact same thing. It calls take, the semaphore sees the count is 2, still good to go. So task B gets in, and the count ticks down to 1. And look, here's task C, ready to grab that last available spot. It takes the semaphore and boom, the count is now 0. We're at full capacity, all slots are taken. So what happens now? What if task D rolls up? It tries to take the semaphore, but this time the count is 0. The semaphore basically says, nope, sorry, we're full. So task D can't go anywhere. It gets blocked. It's just sitting there waiting patiently for a spot to open up. Okay, now let's say task A is done with its work. Before it leaves, it performs a give or post operation. All that does is increment the semaphore's count back up to 1. And that's the signal. The system sees the count is no longer 0, so it wakes up our waiting task D, which can now finally take that newly freed spot and get to work. Now, using a semaphore as a simple gatekeeper like this is fine. It works. But honestly, it's not where they're most powerful. The real magic of a semaphore, its true strength, is in a completely different pattern, signaling. And this is where they absolutely shine. Think of them as the perfect traffic director for something called the producer-consumer pattern. It's a super common design where you have some tasks, the producers, that are creating data or work, and other tasks, the consumers, that process that data. So here's how it works on the producer side. The producer does its job, right? It creates some data and drops it into a shared buffer. And then it calls give on the semaphore. Notice it's not taking anything, it's giving. It's basically raising a flag and shouting, hey, I just dropped off some new work. Every time it calls give, that semaphore's count goes up by 1. So in this model, the count isn't just a gatekeeper. It's actually keeping track of how many items are sitting in the buffer, ready to be worked on. Now, let's look at the consumer. Before it even thinks about touching that buffer, it calls take on the semaphore. If the count is 0, what does that mean? It means there's no work to do. So the consumer just waits. It goes to sleep. But if the count is greater than 0, it knows for a fact there's data waiting, so it proceeds to grab it. And as soon as the consumer takes from the semaphore to go process an item, the count gets decremented. This whole cycle is just beautiful. The producer signals work is ready, and the consumer's take operation is its way of saying, I'm handling one item. It's an incredibly clean and efficient way to keep these tasks perfectly in sync. So you see, this whole signaling thing, that is the absolute key difference between a semaphore and a mutex. Let's put them side by side and make it super clear. Okay, look at this. A mutex is all about locking and what we call mutual exclusion. This means it has a sense of ownership. The same task that locks the mutex must be the one that unlocks it. You can't have one task lock a door and another one unlock it. But a semaphore? It's all about signaling. It has zero concept of ownership. That's why one task the producer can give and a totally different task the consumer can take. We also see priority inheritance here, which is a feature mutexes often have to solve some tricky scheduling problems. The bottom line is they are different tools for completely different jobs. And this is so important, I want to call it out specifically. You might look at a binary semaphore, one that can only count to 1, and think, hey, that's just a mutex. But no, it's absolutely not. Why? Because of that ownership rule. Even a binary semaphore can be given by one task and taken by another. It's still a signal, not a lock. All right, so now that we've cleared all that up, when do you actually pull a semaphore out of your toolbox? What are the classic use cases? Well, for one, they are perfect for signaling from a really low-level thing like a hardware interrupt up to a regular task. We've already seen they are the textbook solution for any producer-consumer problem. They're also great for managing a pool of identical resources. That's kind of like our first example with the 3 slots. And finally, they're a really elegant way to have one task do some big initialization and then signal to a bunch of other tasks, okay, everything's ready, you can start now. So there you have it. A semaphore isn't a bucket of keys. It's a powerful, flexible signaling mechanism. But that brings up a really interesting design question, doesn't it? For that whole producer-consumer thing, couldn't you just use a message queue? I mean, it could handle the signaling and the data transfer all in one go. Which one is better? You know what? That sounds like a great topic for our next deep dive.